we're going to be taking a look at hyperbolic functions. Hyperbolic functions play an important role in engineering and a lot of real-world applications of calculus. Today we're going to get the introductory level definitions and basic ways of how we work with these functions. And they feel a little bit different, a little bit odd. It takes a little bit of time getting used to them. Let's just start out with the basic definitions of these. And one of the reasons that they feel odd is because we use trigonometric words when we define these. We talk about a hyperbolic cosine. So this is not cosh, this is cosine h. Now, a lot of people will say cosh and sine h when we read them, and that's fine, but just keep in mind that this really is putting together two different words. This is cosine and h for hyperbolic cosine. And this is our definition for the hyperbolic cosine of x. So, hyperbolic cosine of x is this, it feels like an average, except for, it is in fact, cosine of h is an average. This should have a plus. E to the x plus e to the negative x over 2. It's like the average of the e to the x and the e to the negative x. Sine, hyperbolic sine of x is similar, but we're taking the difference rather than the sum. The rest of them behave just like you would hope as far as the relationship with our standard trigonometric functions. Tan h is sine h over cosine h of x. And the rest of them, from secant and cosecant and cotangent, are all exactly what you would expect based on these initial definitions of cosine h and sine h. That's fine. It's really just something to memorize at this point, how these things work. Remember that the cosine is the average, the sine, so it has the plus, and the sine has the negative between the two. When we do that, a lot of things behave just as if we were in trigonometric functions. Some things are a little bit different. So some identities. Our favorite trig identity is x squared plus y squared equals 1. Now, that's not exactly what's happening here. It's slightly different. It's because these things come from the hyperbola x squared minus y squared equals 1, rather than the circle x squared plus y squared equals 1 is where we get trigonometry from. We take the x as the x coordinate, or cosine is the x coordinate as we move around the circle, y is the sine is the y coordinate as we move around the circle. We're actually, when we do hyperbolic functions, we're looking at this hyperbola x squared minus y squared equals 1 rather than the circle. And cos h is the x coordinate as we move along this, sine h is the y coordinate as we move along this. So we actually are starting with this function, which leads us to a different fundamental identity. Because x squared minus y squared equals 1, and x corresponds to the cosine, or cosine h corresponds to the x coordinate, what we have is cos h squared minus sine h squared is 1. That is our fundamental trig identity for hyperbolic functions. And we can actually work this out by using the definitions I gave a minute ago. Okay, so let's use our formulas. This is, remember, e to the x plus e to the negative x over 2, then squared, minus e to the x minus e to the negative x all over 2, squared. If we square this, then we get 4 in the denominator, and we have to think about this as foiling the numerator. So let's FOIL out the left-hand piece. If I FOIL the left-hand piece out, I get e to the x squared. I get 2, I get e to the x times e to the negative x, and then 2 of them. 2 e to the x, e to the negative x. That's the outer and the inner combined. And then the last will be e to the negative x squared. on the right-hand piece, minus, first is e to the x squared. Outer and inner will make now negative because of the minus that's in the middle. 2 e to the x, e to the negative x. And then plus e to the negative x squared. Each of these denominators is now 4. E to the x squared minus e to the x squared cancels. E to the negative x squared minus e to the negative x squared cancels. E to the x times e to the negative x. Well, e to the negative x is 1 over e to the x. So e to the x times e to the negative x is 1. So this is 1. This is 1. And I get 2 minus negative 2, which is 4. So I get 4 over 4, which is 1. Verifying this hyperbolic trig identity. Every other trig identity, hyperbolic identity, can be verified in exactly the same way, either by using this to start with, or by going back to those basic definitions, expanding everything out, and seeing what we get. Okay, what about inverse hyperbolic functions? Okay, these get a little bit complicated, and I'm going to work one out. The rest work exactly the same way. The question is, if y is equal to, let's start with cosine h x. If y is equal to cosine h of x, let's find y inverse. Or if you're more comfortable, how about this? If f at x equals cosine of h of x, let's find f inverse of x. Let's find the inverse function. Now, it shouldn't be a big surprise that we're going to end up getting natural logs, because these are e to the x, right? Cosine of h is essentially a version of e to the x. The inverse function of e to the x is a natural log. So let's see how that works out. So we've got y is equal to cosine hx. Y is equal to e to the x plus e to the negative x over 2. How do we find an inverse function? Remember that we find an inverse function by switching y and x and then solving for y. So that comes down to, let me put that up here. That comes down to x is equal to e to the y plus e to the negative y over 2. My goal is to solve for x, or to solve for y. So we'll multiply by 2. And I get 2x is equal to e to the y plus e to the negative y. And so let's do our tricky algebra. We'll start by moving the 2x over to the right. I'm going to put it in the middle. And then we're going to do something that doesn't seem to make any sense until we get a step ahead. What I'm going to do is I'm going to multiply both sides by e to the y. And again, somebody was clever enough to figure this out. In the end, we just have to see why it works by working through all the way. This is still 0. If I multiply both sides by e to the y, this becomes e to the y squared. This becomes minus 2x e to the y. And this is e to the negative y times e to the y. Just like a few minutes ago, that's 1 over e to the y times e to the y, which is 1. Now we have to recognize this in an odd way as something that looks like ax squared plus bx plus c equals 0. Right? Where the x in this case is e to the y. So this is, if I let x be e to the y, then x squared is e to the y squared, and a is equal to 1. So if x is equal to e to the y, what's going on for this quadratic formula up here is that this is a is equal to 1, because that's 1 times x squared, 1 times e to the y squared. B is equal to negative 2x, right here, so this is b times the e to the y. So e to the y is my variable, something squared, e to the y to the first power, and c is equal to 1. So this is actually a quadratic formula where the variable isn't x, the variable is e to the y. E to the y squared, e to the y, and 1. So we can actually apply the quadratic formula using a, b, and c as given right here. And so if we do that, negative b we get that the variable e to the y, that's what our variable is. Originally it would be x equals negative b plus or minus square root of b squared minus 4ac all over 2a. But the variable here is e to the y, so I get e to the y is equal to negative b, which is positive 2x, plus or minus the square root of b squared, which is 4x squared, minus 4ac. So that's minus 4 all over 2a. Now, this can be simplified more. This is 2x plus or minus the square root of, well, we can factor the 4 out. If I factor the 4 out, x squared minus 1 all over 2. That 4 becomes 2x plus or minus 2 root x squared minus 1 all over 2. 2 simplify out, and I get x plus or minus square root of x squared minus 1. Now, a few things to point out here. No matter what y is, e to anything is positive. So this has to be a positive. And so that means that we're only going to need the positive root here. And also, and x is, since e to the y has to be positive and x is positive too, because remember we were looking on that hyperbola on the right hand side of the hyperbola where we only had positive values of x. Right. So we get e to the y is equal to this. Remember, our goal is to solve for y. We had switched the x and the y's in the original definition. Now we need to solve for y. We do that by taking the natural log of both sides, and then y comes down, and I get y is equal to the natural log of x plus square root of x squared minus 1. So that tells me that we started with the formula for cosine h. We switched x and y's and we solved for y using a big, long, complicated algebra process. This tells me that this is cosine h inverse of x. If you go into our program and open up the ebook, or if you're looking at any of the homework questions and you say, take me to the textbook, view the textbook, you'll see this. You'll see formulas for the other ones worked out as well. And it's always the same process to find these. In the end, you won't have to go through the whole process. You'll just have to be able to use the final result. And as I pointed out, we have a natural log. It's kind of complicated looking, but it's not surprising based on the fact that the hyperbolic, cosine, and sines have e to the x in them. All right, so we can also ask. So we started with the definition for hyperbolic, sine, cosine, tangent, and so on. We looked at the inverse, at how we can calculate inverse functions. We can also talk about derivatives and integrals. These work similar to the derivatives and integrals of trigonometric functions, but it's not exactly the same. So let's start with our sine. Right, so let's take the derivative of sine hx, which is the derivative of e to the x minus e to the negative x over 2. Taking the derivative of this, well, that's just the derivative of e to the x over 2 minus e to the negative x over 2. Separately, e to the x is e to the x. 2 is 2. E to the negative x is negative e to the negative x over 2. Minus minus makes plus. And we recognize this as the formula for hyperbolic cosine. So the derivative of a hyperbolic sine is hyperbolic cosine. And that's great, because that's how we're used to trig functions. Derivative of sine is cosine. The derivative of cosine, though, doesn't quite work the same. And so we have to be a little bit careful when we're looking at hyperbolic functions. If I want the derivative of hyperbolic cosine, that's derivative of e to the x plus e to the negative x over 2. When I take these derivatives, the e to the x is e to the x, now the minus comes down, and it's minus e to the minus x, still over 2. There's no extra negative sign out front, because the negative really serves to change the sign in there, and this is hyperbolic sine on its own. So derivative of hyperbolic cosine is just hyperbolic sine. That's different than in trig, because derivative of cosine is negative sine. That negative does not show up when we're looking at the hyperbolic functions. I'm not going to work this one out. Just to summarize so far, derivative of hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is hyperbolic sine, without a negative. Derivative of hyperbolic tangent is hyperbolic secant squared. This is exactly what we would expect it to be. Derivative of tangent in a regular trig is secant squared. This one is true. There's no plus. There's no negative sign that gets in the way or is different. If you just work out the formula for this one, this is what you're going to get in the end. And finally, we're going to look at derivatives of the inverse hyperbolic functions. And so again, these take some creative algebra to work out that you will not have to reproduce, but you will just have to be able to use the final result. But I do want to work out one of them for you and explain it fully. So let's find the derivative of the inverse hyperbolic sine function. Okay, so that's what we want. We want to find the derivative of this. So we're going to start with y equals sine h inverse of x, which is the same thing as saying, remember that if y is equal to sine inverse h of x, I can apply sine h to both sides, or you can think about that as switching the x and y's to get rid of the inverse. I get sine hy is equal to x. We're going to take the derivative of both sides. This is sort of an implicit differentiation, if you want to think about it like that. We're taking the derivative of both sides of these with respect to x. If I take the derivative of the left with respect to x, then I get cosine hy. But since this is implicit differentiation, I need to take the derivative of the inside. Derivative of the inside is dy dx. The derivative of the right-hand side is the derivative of x, which is just 1. So then we're going to bring this one over to the right, and I get dy dx is 1 over cosine hy. All right, so far so good. Let's remember our fundamental hyperbolic function identity, which is that cosine h squared x minus sine h squared x is equal to 1. Solve for cosine h, that I get cosine h x, bringing the sine h over to the right hand side and then taking the square root, I get 1 plus, or I get sine h squared x plus 1 by moving this over to the right and then taking the square root. So if I plug that bit back in up here, that becomes 1 over square root of sine h squared y plus 1, not x because we're using y here. So the formula holds with y in place of x. Alright, that's good, but remember that we started with y is equal to, well, we started with y is equal to sine h inverse, then we switched to x and y's, so we actually had x is equal to sine h y. Since x is equal to sine h of y, that means that this is 1 over square root of x squared plus 1. And that is the derivative, dy dx. So let me just summarize what we found. We went through this whole process. We started with y equals sine h inverse of x, and we found that y prime is 1 over the square root of x squared plus 1. Again, we can do something similar for starting with the inverse cosine and inverse tangent and any of the other ones. I'm not going to work out the details for all of those. I did just want you to see one of those worked out. And that's the fundamental ideas that we have to be aware of for the hyperbolic functions, and I'll see you next time.